This is video 4 of topic 9 on snow hydrology. In this video, we'll talk about the snowpack. There's a number of important properties and characteristics of snow and snowpacks that we need to know. So first of all, what is a snowpack? A snowpack is a porous medium of ice and air, and quite often liquid water as well. It's generally composed of layers of different types of snow, and the characteristics are more or less homogeneous within a single layer. It's made of ice in the form of crystals and grains that are usually bonded together, and this forms a texture with some degree of strength. So here's an example of a snowpack. You can see very clearly the different layers corresponding to different snowfalls. Again, you can see very clearly all of these layers. Together, this makes up a snowpack. Snowpacks are not static. Over time they change. And so over time, a snowpack undergoes compaction as ice crystals metamorphose and settle. As the winter progresses, the snow depth generally decreases while the density increases. The cause is that snow metamorphoses from low density, fine grains to high density, coarse grains based on the diurnal or daily temperature cycle. Small grains begin to melt and then they refreeze into rounded, large-grained snowpacks. The degree of metamorphism depends on the climate and whether the snow is wet or dry. And finally, the amount of snow water equivalent shouldn't actually change as this occurs unless it's reduced by sublimation. Let's talk about how this progression occurs. When the ground is first covered by snow, other than in permafrost areas at high latitudes or high elevations in mid-latitudes, the ground is mostly warm, or it's near freezing. This is true even when the air is very cold because snow is a good insulator. Therefore, there's usually liquid water in the snowpack, and it's common for snow near the ground to remain relatively warm for most of the winter. This allows depth hoar to form at the base of the snowpack because of a large temperature gradient between the warm ground and the cold snow surface. And so what happens is rising water vapor freezes onto existing snow crystals. This usually requires a thin snowpack combined with a clear sky or low air temperature. And depth hoar then grows best at temperatures from about -2 through to about -15 degrees Celsius. Depth hoar consists of sparkly, large-grained, faceted, cup-shaped crystals that can be up to 1 centimeter in diameter. Larger grain depth hoar is more persistent and can last for up to weeks at a time. It's strong in compression and weak in shear. This is a very important point because it can fail in the form of collapsing layers with fractures propagating long distances. That should sound like an avalanche, and so almost all catastrophic avalanches fail on depth hoar. There's a number of really interesting videos here that you can check out that'll show you these fracture propagations and the effect of catastrophic avalanches. Here's an image of a snowpack. You can see at the base depth hoar, and then actually there are different layers of depth hoar, and so here's another one here, and then here's surface hoar or frost at the top. Here's an image of what depth hoar actually looks like. You can see clearly that these are the faceted cup-shaped crystals I was describing. Here again is another image of the same. We also need to talk about the density of snow cover, and so here's a number of different snow types. Here's their various densities, and then here is the amount of snow you need to melt to get 1 centimeter of snow water equivalent. Wild snow is the very light, fluffy stuff that you find in very dry conditions. Here's ordinary snow, settling snow, then wind-toughened snow, wind slab, and then firn snow. You can see the density varies really significantly from about 1% of the density of water all the way up to about 70% of the density of water. For the very lightest wild snow, we can have up to almost 1 meter of snow being melted to produce only 1 centimeter of water. In terms of definitions, a wind slab is relatively stiff, hard snow, And then firn snow is rounded, well-bonded snow that's older than a year. Here are some examples of snow grain shapes. This is a sector plate with some rhyming around the edges. This is early rounding. This is faceted growth. Okay, these are all very small scales. So here we're looking at a magnification of 230 times. This bar here is 0.1 millimeters. And this is early sintering or bonding of the different crystals. Again, very small. Then these are a larger scale. This is 1 millimeter for these bars here. And so here we're looking at wind-blown grains, so they're being rounded off. This is melt and freeze with no liquid water present. So you can see it's much less extreme than this case here, where we've had melt and then freeze with liquid water. This is faceted layer growth, so this is where we're beginning to get depth hoar, and then this is an example of depth hoar. Another important characteristic for the snowpack is the grain size. And so here's a number of different scales. The average size of the characteristic grains within a mass of snow is given here, and these values represent the greatest extension in millimeters. We can rate grain sizes very fine, fine, medium coarse, very coarse, or extreme, and here we go from 0.2 millimeters all the way up to greater than 5 millimeters. We also should look at the amount of liquid water content in the snowpack. This is particularly important for the next videos where we start talking about snowmelt and snowmelt modeling. So here's a table that classifies various different types of snowpack by their liquid water content. We can have dry snowpacks, and this will be below 0 degrees Celsius, but it can occur at any temperature up to equal to 0 degrees Celsius. This is approximately 0% liquid water, and so there's very little tendency for the snow grains to stick together. You can pick it up and it just falls out of your hand. Moist snow occurs at a temperature of 0 degrees. The water won't be visible even at a magnification of 10 times, but you'll begin to notice that it'll stick together. And so this is a liquid water content of 3% or less. We're now getting into wet snow, so this is where the water can actually be seen at a 10 times magnification by its meniscus between the grains. But if we squeeze the snow, we can't squeeze out liquid water. And so this will range between 3 and 8%. We then get to very wet snow, again at 0 degrees Celsius, and here water can actually be pressed out by squeezing the snow, but there's an appreciable amount of air still in that snowpack. And so here we're looking at 8 to 15% water, liquid water. And then of course we're all familiar with slush. Again, the temperature is 0 degrees Celsius, but here the snow is now flooded with water, and it contains a relatively small amount of air, and this is where the percentage of water will be 15% or higher. This ends video 4.